The sound of the metal is the first thing that changes. It starts as a faint, rhythmic ticking, like a clock counting down in a room where the air has grown too heavy to breathe. But as the mercury slides past zero, past -20, and finally settles at a bone-breaking -40 degrees Fahrenheit, that ticking transforms. It becomes a sharp, crystalline snapping, the sound of galvanized steel contracting against its own structural ribs. It is the sound of a building trying to shrink away from the sky. Outside, the wind is moving at 70 miles per hour, a relentless, invisible wall of kinetic energy that is currently scouring the landscape of every calorie of heat it can find. If you were standing out there, the moisture on your eyeballs would crystallize in seconds, but you aren't out there. You are standing in the center of a paradox, a warm, silent sanctuary of engineered survival. Now, picture this. You are inside a 1941 design, a semi-cylindrical relic of the Second World War, a Quonset hut. In any other scenario, this steel shell would be your tomb. In a storm of this magnitude, the worst the region has seen in 34 years, an uninsulated steel hut is nothing more than a prefabricated coffin. The physics are undisputed. Steel has a thermal conductivity of roughly 50 watts per meter Kelvin. It does not hold heat. It hunts for it. It reaches through your layers of wool and fleece to suck the warmth directly out of your marrow, radiating that energy into the black maw of the blizzard. And yet, as the wind screams against the outer walls, the air around you remains a steady, defiant 72 degrees. Here's what everyone missed. The secret isn't in the insulation of the hut alone. It is in the architecture of the nest. You are standing inside a house, built inside a barn. This is the Matryoshka Protocol, a nested thermal envelope where the outer structure acts as a sacrificial shield, a mechanical buffer that breaks the back of the wind before it can ever touch your living space. We have created a world where the Bernoulli effect, the physics of air, moving at high speed, stripping heat from a surface, simply ceases to exist for the inner dwelling. Think about that for a second. While the world outside is an apocalyptic blur of white noise and lethal cold, the air in the gap between this hut and the barn is almost perfectly still. It is a plenum space, a dead air buffer that changes the entire thermodynamic equation. But to understand how we got to this point of mechanical triumph, we have to look at the failure of the original design, and the hubris of the men who thought they could conquer the elements with nothing more than a thin sheet of corrugated zinc. The story of the Quonset hut begins in the frantic early days of 1941 at the Quonset Point Naval Air Station in Davisville, Rhode Island. The United States military needed a miracle of logistics. They needed a shelter that could be manufactured by the thousands, crated into flat packs, and shipped to the steaming jungles of the South Pacific or the frozen wastes of the Aleutian Islands. They looked across the Atlantic at the British Nissen hut, a simple, arched structure, born in the trenches of the First World War. And they decided they could do better. They wanted something lighter, faster, and more versatile. The result was the T-rib Quonset hut, a masterpiece of geometric efficiency. By using the arch, the engineers at the George Fuller Company created a structure that could support incredible snow loads, while using a fraction of the material required for a traditional peaked roof. The galvanized steel was resistant to rot, termites, and fire. It was the ultimate set-it-and-forget-it architecture for a global war. But there was a hidden cost to this efficiency, a cost that many veterans would spend the next several decades paying in discomfort. Let that sink in. The very reason the military loved the Quonset hut, its thin, lightweight steel skin, was exactly why it was a thermodynamic nightmare. In the 1940s, fuel was often more abundant than high-performance insulation. If a hut was cold, you simply cranked the oil stove until the steel ribs glowed a dull cherry red. You fought the environment with raw, brute force consumption. But in a survival situation, in the face of a 34-year storm where the grid has vanished and your fuel supply is finite, brute force is a losing game. If you want to understand the deep engineering of how we turned this icebox into a thermal fortress, how we calculated the exact air gap required to turn a drafty barn into a stagnant air buffer, and most importantly, how to avoid the deadly carbon monoxide traps that come with nesting these structures. You need to see the full audit. Hit the subscribe button now and join us as we deconstruct the mechanics of the Matryoshka method. Because the numbers don't lie, and in a blizzard, math is the only thing that stays warm. To truly appreciate why a standard Quonset hut fails in extreme cold, we have to talk about the abrasive reality of galvanized zinc and the science of the heat sink. When you touch the interior wall of an uninsulated hut in midwinter, you aren't just feeling cold metal. You are feeling the laws of thermodynamics aggressively seeking equilibrium. Because steel is such an efficient conductor, it acts as a thermal bridge. Even if you put a heater in the middle of the room, the steel ribs act like cooling fins on an engine, constantly pulling that heat away and dumping it into the outside air. In the 1940s and 50s, surplus Quonset huts were sold to farmers and veterans for pennies on the dollar. They became the backbone of rural America, workshops, hay barns, and even low-cost housing. But the people living in them quickly discovered the icebox effect. In the summer, the sun turned the arched roof into a giant radiator, baking the occupants in a convection oven of trapped air. In the winter, condensation would form on the cold interior steel, dripping down the walls and ceiling like a slow, freezing rain. This wasn't just uncomfortable. It was destructive. The moisture would rot out the wooden end walls and rust the very bolts holding the structure together. The military's solution had been disposability. If a hut became uninhabitable, you simply built another one. But for the modern homesteader or the survival engineer, that is not an option. We have to look at the hut not as a standalone building, but as a core component in a larger machine. The numbers don't lie. If you take a standard 16 by 36 foot Quonset hut and place it in an open field during a -40-degree event, you would need nearly 100,000 British thermal units of heat per hour just to keep the interior above freezing. That is a staggering amount of energy. You would be burning through a 20-pound propane tank every 4 to 5 hours. It is unsustainable. It is a death sentence. But when you place that same hut inside a secondary structure, a traditional pole barn, or a larger timber frame, everything changes. The outer barn becomes the first line of defense. It doesn't have to be insulated. It just has to be tight. By stopping the wind, you are eliminating the most dangerous factor in heat loss: convection. In the world of thermal mechanics, we talk about the R value of materials, their resistance to heat flow. A single sheet of steel has an R value that is effectively 0, but a 1-inch layer of stagnant air, that has an R value of nearly 1. It sounds small, but in the world of physics, stagnant air is one of the best insulators in existence. The problem is that air is almost never stagnant. In a normal building, the air is constantly moving, driven by temperature differences and wind pressure. This is where the Matryoshka audit begins. We aren't just putting a hut in a barn, we are engineering a plenum space. This is the air gap between the outer barn wall and the inner hut shell. By sealing the barn and preventing the wind from whistling through the cracks, we create a pocket of air that the wind cannot touch. The barn takes the brunt of the 70-mile-per-hour gusts. The barn vibrates. It moans under the structural load. It absorbs the kinetic energy of the blizzard. But inside that barn, the air surrounding the Quonset hut is remarkably calm. Imagine the difference between standing in a -40-degree wind and standing in a -40-degree room with no wind at all. The difference to your body is the difference between life and death. But for the building, the difference is even more profound. Without the wind chill factor, the effective temperature the hut has to fight is significantly higher. In our specific configuration, we discovered something incredible during the first night of the Great Storm. While the outside thermometer was plummeting toward 40 below, the air inside the barn, the air in that plenum space, was holding steady at 15 degrees above zero. Think about that. Without a single heater running in the barn, the mere act of nesting one building inside another had created a 55-degree temperature differential. Why? Because the barn was capturing the tiny amount of waste heat that escaped from the insulated hut. In a normal house, that heat would be blown away by the wind, the second it passed through the wall. But here, the heat was trapped in the buffer zone. It was preheating the air that surrounded the hut. We had created a self-regulating microclimate. But this triumph of engineering comes with a hidden, lethal danger. When you nest a living space inside another structure, you are effectively creating a sealed box. If you are using any form of combustion for heat, whether it's a wood stove, a propane heater, or a diesel heater, you are creating exhaust. In a standard house, that exhaust goes up the chimney and vanishes into the sky. But in a nested structure, if your venting isn't perfect, that carbon monoxide can leak into the barn's plenum space. Instead of escaping into the atmosphere, the deadly gas pools in the stagnant air around your hut. It can then be drawn back into your living space, through the very air intakes you rely on for oxygen. It is the silent executioner of the survival world. We have seen cases where people built beautiful, warm, nested cabins, only to never wake up because they forgot the physics of the double roof vent. We had to design a specialized Type L double-walled venting system that passed not just through the roof of the Quonset hut, but through the roof of the barn as well, with a specific 210-3 clearance to ensure that the wind outside would create a vacuum, pulling the exhaust out rather than letting it settle. We had to ensure that the air being fed into the stove was piped in from the extreme exterior of the barn, not just from the gap. Every joint in the steel, every rib in the arch, had to be considered not just as a structural member, but as a part of a thermal machine. The abrasive texture of the galvanized zinc, which once felt cold and industrial, now felt like the hull of a submarine, a protective barrier between us and an environment that was fundamentally hostile to human life. The hollow echo of the hut, which once sounded like an empty hangar, was now muffled by layers of closed-cell spray foam and the deep, heavy silence of the surrounding barn. As we sat there, listening to the roar of the blizzard outside, we realized that we weren't just surviving a storm. We were witnessing the ultimate validation of a 1941 geometry updated with 21st-century thermodynamics. We had turned a historical relic into a life support system, and as the storm outside intensified, we knew the real test was only just beginning. The first shovel hit the dirt in late August. It was a dry, dusty sound, a far cry from the wet, heavy slap of the mud that would define the autumn to come. We weren't just building a foundation. We were engineering a thermal break between the living space and the indifferent basalt of the Earth's crust. Most people think of a foundation as a simple structural necessity, a way to keep a building from sinking into the loam. But when you are designing for a -40-degree event, the foundation is actually your first line of defense against the great heat thief. The Earth is a massive battery. It holds a constant temperature of roughly 55 degrees Fahrenheit. Once you get below the frost line, in most places in the north, that frost line sits at 48 inches. If you build a steel hut directly on a concrete slab that is exposed to the outside air, that slab becomes a massive radiator. Only it is radiating your warmth directly into the frozen ground. To stop this, we had to rethink the entire geometry of the floor. We excavated down to 60 inches, well below the historical frost line of our region, and laid down a bed of compacted 3/4-inch crushed stone. On top of that, we placed 4 inches of high-density extruded polystyrene insulation, an R value of 20, to ensure that the concrete slab of the hut would never actually touch the cold earth. Now, picture this. A floating island of concrete, 6 inches thick, reinforced with number 4 rebar on 12-inch centers, completely wrapped in a thermal blanket. This is the stage upon which the Matryoshka Protocol would be performed. But before the first steel arch of the Quonset hut could be raised, we had to build the sacrificial shield, the outer barn. The barn was never meant to be a living space. Its job is to be the brute force bodyguard for the inner dwelling. We chose a traditional pole barn design, using 6x6 pressure-treated timbers set 8 feet apart. These aren't just posts. They are the anchors that hold the shield against the 70-mile-per-hour winds we knew were coming. We skinned the barn in 29-gauge steel siding, but we didn't just screw it on and call it a day. Every lap joint was sealed with a double bead of butyl tape. We were building a pressurized box. Here's what everyone missed. If the outer barn has even the smallest leak, The Bernoulli effect will find it. As the wind screams over the peak of the barn, it creates a zone of low pressure on the leeward side, literally sucking the air out of the building. If you have leaks, the barn will breathe inhaling freezing air and exhaling your precious trapped warmth. Once the barn was capped with its heavy-duty steel roof, we finally had a controlled environment to begin the assembly of the inner core. This is where the 1941 military engineering meets 21st century thermal management. The Quonset Hut arrived in flat-packed crates, hundreds of corrugated steel panels, each weighing nearly 60 pounds, and thousands of grade 5 carriage bolts. Assembling a Quonset Hut is a rhythmic, almost meditative process of mechanical repetition. You start with the base channel's heavy-duty steel tracks bolted directly into the concrete slab. Then, you begin the arches, one panel at a time, overlapping the last by 2 inches, secured by a bolt every 6 inches along the seam. The sound of the impact wrenches echoing inside the barn was deafening. A sharp, metallic clack, clack, clack that signaled another inch of the fortress was complete. Think about that for a second. There are over 3,000 bolts in a 36-foot hut. Each one of those bolts represents a potential thermal bridge, a tiny highway for heat to escape. If we had built this hut outside, every single one of those 3,000 bolts would be a point of condensation, a place where the -40-degree air outside would meet the 70-degree air inside, creating a localized rainstorm of frozen meltwater. But because we were building inside the barn's plenum space, the temperature difference was already being mitigated. As the arches rose, we maintained a consistent 18-inch gap between the outer edge of the Quonset ribs and the interface of the barn's timber frame. This 18-inch void is the Matryoshka gap. It is the most critical dimension in the entire project. Why 18 inches? Because it is wide enough to allow a human to crawl through for maintenance, but narrow enough to prevent large-scale convection loops from forming. If the gap is too wide, say, 5 or 6 feet, the air inside will begin to circulate in a giant circle, picking up cold from the barn wall and dropping it onto the hut wall. At 18 inches, the air remains sluggish. It stays put. It becomes stagnant. The numbers don't lie. The R value of 18 inches of stagnant air is nearly equivalent to 18 inches of solid wood. We were effectively wrapping the hut in a wall of air that was 2 feet thick. But we weren't done. The steel shell of the hut, while structurally magnificent, is still a thermal disaster. It is a 1940s icebox. To fix that, we turn to the chemistry of the modern age. Closed-cell spray polyurethane foam. Applying spray foam to galvanized steel is a visceral experience. You are wearing a full-face respirator, a Tyvek suit, and heavy gloves. The 2-part chemicals isocyanate and resin are heated to 130 degrees Fahrenheit in the proportioning machine and pumped through 200 feet of hose. When the chemicals hit the mixing tip of the spray gun and atomize against the steel, they undergo an exothermic reaction. The liquid hits the metal, and within 3 seconds, it expands 30 times its original volume, turning into a rigid plastic honeycomb. The smell is sharp, a mix of ozone and burnt sugar, and the sound is a constant high-pressure hiss. We applied 3 inches of this foam directly to the interior of the steel arches. Because it is closed-cell, the foam doesn't just insulate. It acts as a vapor barrier. It seals every single one of those 3,000 bolt holes. It bonds to the galvanized zinc with such tenacity that it actually increases the structural rigidity of the hut by nearly 20%. Let that sink in. The insulation wasn't just keeping us warm, it was turning the steel arches into a composite structure that could handle even greater loads. We calculated that 3 inches of this specific foam gave us an R value of 21. On its own, in a standard house, that would be respectable. But when you layer that R value of 21 inside the stagnant air gap of the barn, you aren't just adding the numbers together. You are multiplying the efficiency. We spent weeks meticulously spraying the foam, ensuring that there was not a single square millimeter of exposed steel. We paid special attention to the T-ribs, the structural supports that provide the hut with its characteristic strength. These ribs are the most dangerous part of a Quonset hut because they protrude further into the room. If you don't cover them with at least 2 inches of foam, you will get ghosting, a phenomenon where the cold from the outside steel travels down the rib and causes moisture in the air to freeze on the tip of the rib, creating a line of frost that runs the entire length of your ceiling. Once the foam was cured, the interior of the hut looked like the inside of a massive white cavern. The acoustic change was immediate. Before the foam, the hut was an echo chamber. Every footstep on the concrete sounded like a gunshot. After the foam, the silence was heavy, almost oppressive. It felt as though we were standing in a room made of wool. This acoustic deadness is the first sign of a perfectly sealed thermal envelope. But a cavern with no air is a tomb. We had to address the most complex part of the Matryoshka method, the penetration of the dual envelope system. Every pipe, every wire, every vent that leaves the hut has to pass through the 3-inch foam layer, the 18-inch air gap, and the outer barn wall. If you do this incorrectly, you create a chimney effect in your walls, where warm air escapes the hut and is replaced by a jet of freezing air from the gap. We used 4-inch PVC sleeves for all penetrations, which were then foamed in to ensure a perfect seal. For the electrical service, we ran the main lines through the floor slab to avoid puncturing the walls altogether. But the real challenge, the engineering hurdle that keeps survivalists up at night, was the heating system. In a normal Quonset hut, you'd just stick a wood stove in the corner and run a pipe through the roof. In our nested system, that's a recipe for a house fire or carbon monoxide poisoning. We chose a sealed combustion diesel heater, originally designed for the maritime industry. These units are incredible. They have a 2-stage heat exchanger. They draw their combustion air from a dedicated pipe that goes all the way to the exterior of the barn, and they vent their exhaust through a separate, double-walled pipe that does the same. The air you breathe inside the hut is never in contact with the air used for the fire. Think about that for a second. The heater is a closed loop. It takes oxygen from the frozen world outside the barn, uses it to burn fuel, and dumps the toxic exhaust back outside. The heat is transferred through a series of aluminum fins inside the unit, and a fan blows the clean, warm air into the room. To install this, we had to core drill a hole through both the inner steel of the hut and the outer siding of the barn. We used a Type L vent pipe, which features an inner liner of stainless steel and an outer liner of galvanized steel, separated by 1 inch of mineral wool insulation. This pipe is rated for temperatures up to 1,000 degrees Fahrenheit. As it passes through the 18-inch Plenum Space, the pipe is exposed to that stagnant air. If the pipe were to fail, the exhaust would fill the barn. To prevent this, we installed a secondary sleeve of 6-inch galvanized ducting around the vent pipe as it crossed the gap, creating a pipe within a pipe within a structure within a structure. It was a redundant, obsessive, and expensive way to vent a heater. But in the context of the Matryoshka audit, redundancy is the only currency that matters. As the final pieces of the interior end walls were being framed, using 2x6 Kyline dried lumber and stuffed with mineral wool bats for additional sound dampening and fire resistance, the weather began to turn. The long golden days of September were replaced by the gray, biting winds of October. The temperature in the barn began to drop, but inside the hut, without a single heater turned on, it remained a steady 65 degrees. The thermal mass of the concrete slab, coupled with the R value of 21 foam and the stagnant air of the plenum, was already holding onto the summer's heat like a battery. We watched the barometer. We watched the weather stations in the Dakotas and Minnesota. We saw the pressure gradients beginning to stack up, a massive high-pressure system from the Arctic colliding with a moisture-rich low-pressure system from the Gulf. It was the classic setup for a bomb cyclone, a storm that would drop the pressure so fast it would effectively create a winter hurricane. Most people in the area were boarding up windows or heading south. We did the opposite. We moved into the hut. We stocked the shelves with 3 months of food. We checked the seals on the diesel tanks, 2 500-gallon reservoirs buried in the earth next to the foundation, connected to the hut by pre-insulated PEX piping. The final step of the construction was the pressure test. We used a blower door, a giant fan that seals into the front door frame to depressurize the hut. We wanted to see how much air was leaking. The industry standard for a tight modern home is roughly 1.5 air changes per hour. Our Matryoshka hut, it clocked in at 0.3. It was effectively an airtight vessel. We were ready. The construction of the Matryoshka fortress was a rejection of the fast and cheap military philosophy of 1941. We had taken the arched geometry of the Quonset, a shape designed for speed and utility, and we had wedded it to the most advanced thermodynamic principles of the modern age. We hadn't just built a shelter. We had built a mechanical equilibrium. When the first flakes of the 34-year storm began to fall, they didn't hit our windows. They hit the barn. We couldn't even see the snow. All we could hear was the faint, muffled hum of the wind against the outer steel, a sound that felt miles away. Inside the hut, the air was still. The temperature was a perfect 72 degrees, and the only thing moving was the steady, rhythmic tick of the diesel heater's fuel pump. The Matryoshka method was no longer a theory. It was a physical reality. The sacrificial shield was taking the beating, the Plenum Space was breaking the convection, and the inner core was holding the line. We were sitting in the middle of a thermodynamic triumph, waiting for the world outside to turn white. And as the wind speed climbed toward 50, 60, 70 miles per hour, we realized that the engineering wasn't just about survival. It was about the absolute, defiant luxury of remaining unchanged, while the world outside disintegrated into chaos. But as the warmth settles into the bones of the structure, a new, more sinister physics begins to play out in the darkness of the Plenum Space. We have to talk about the invisible killer, the one thing that can turn an engineered masterpiece into a tomb before you even realize the air has changed. When you nest a living envelope inside a secondary shell, you are not just managing heat. You are managing the very chemistry of the atmosphere you breathe. Most people understand the basic danger of carbon monoxide, that odorless, colorless, and tasteless byproduct of incomplete combustion. But what they fail to grasp is how the Matryoshka geometry creates a unique and deadly reservoir for this gas. In a traditional home, a leak in a furnace vent is dangerous, but the gas often has multiple paths to dissipate through the porous layers of a standard attic or crawlspace. In our nested system, the 18-inch gap between the Quonset hut and the barn acts as a giant, stagnant lung. If the exhaust from our diesel heater or a backup propane unit were to breach its primary seal, it wouldn't just vanish into the sky. It would fill that 18-inch void, pooling around the exterior of the hut like a rising tide of invisible poison. Because the inner hut is under a slight negative pressure, driven by the very fans that circulate our air, the structure would begin to inhale its own exhaust. This is why the engineering of the ventilation system had to be flawless, governed by the strict, uncompromising logic of the 2-10-3 rule. This isn't just a guideline. It is a mathematical mandate for survival in a dual-envelope structure. The chimney must extend at least 3 feet above the point where it penetrates the roof, and it must be at least 2 feet higher than any part of the building within a horizontal distance of 10 feet. When you have a hut inside a barn, you aren't just dealing with one roof. You are dealing with a complex aerodynamic profile. If the chimney is too short, the high-velocity winds of a 34-year storm will create a high-pressure cap over the vent, effectively pushing the exhaust back down the pipe and into your living room. Think about that for a second. The very wind that is trying to freeze you to death is also trying to choke you. To combat this, we utilized a sealed combustion protocol that treats the heater as if it were on a different planet. The intake air, the oxygen required for the flame, is drawn through a dedicated 3-inch insulated pipe that bypasses the barn's interior entirely. It reaches out through the north wall of the barn, into the teeth of the gale. The exhaust is carried away by a double-walled Type L vent, featuring an inner liner of 316 stainless steel. This inner liner is designed to withstand the corrosive sulfuric acid that can condense from diesel exhaust, while the outer galvanized layer remains cool enough to prevent the 3 inches of spray foam from melting. But the numbers don't lie. and the numbers told us that mechanical seals can fail. Vibrations from 70-mile-per-hour winds can loosen a bracket. Extreme temperature fluctuations can crack a weld. That is why the Matryoshka audit requires a dual-path detection system. We installed industrial-grade carbon monoxide sensors, not just inside the hut, but inside the Plenum Space itself. If even 5 parts per million of carbon monoxide are detected in that 18-inch gap, a high-decibel alarm sounds. And the fuel supply to the heater is mechanically severed by a spring-loaded solenoid valve. We are monitoring the air that surrounds our air. This level of obsessive safety is the only way to justify the thermodynamic gain of the nested structure. And that gain is rooted in the concept of thermal mass balance. Inside the hut, we aren't just heating the air. We are heating the concrete. Remember that 6-inch thick floating slab? Those thousands of pounds of high-strength concrete we poured over the foam insulation? That slab is our thermal flywheel. It takes hours for the diesel heater to bring that mass up to 72 degrees. But once it is there, it becomes a massive battery of stored energy. Even if the heater were to fail completely in the middle of a -40-degree event, the physics of the Matryoshka system dictate that the temperature inside the hut would only drop by about 1 degree every 4 hours. The concrete is radiating heat upward, while the stagnant air in the plenum space is preventing the wind from stripping that heat away. We have achieved a state of thermodynamic equilibrium where the environment outside has almost no immediate impact on the environment inside. It is the ultimate expression of mechanical independence. And then, the storm arrived. It didn't begin with a roar. It began with a silence so profound, it felt as though the earth had stopped spinning. The barometer on the wall, a precision instrument calibrated in millibars, began to dive. It wasn't a gradual slide. It was a collapse. In the span of 6 hours, the atmospheric pressure dropped by 24 millibars. A classic bombogenesis event that signaled the arrival of a winter hurricane. Now, picture this. You are sitting at a small wooden table inside a steel arch. The lights are dim. The only sound is the rhythmic metallic thump-click of the fuel pump. Outside the hut, but still inside the barn, the air is an eerie, frozen 15 degrees. But outside the barn, the world has vanished. The first true gusts of the 34-year storm hit the structure at 4 o'clock in the afternoon. It didn't sound like wind. It sounded like a freight train derailment occurring just inches from your head. The 70-mile-per-hour winds slammed into the 29-gauge steel siding of the barn, and for the first time, the structural moan began. This is the sound of a building reaching its limit. The 6x6 pressure-treated posts, buried 5 feet deep in the earth, began to flex. The steel siding vibrated with such intensity that it created a low-frequency hum, a subsonic thrumming that you could feel in your teeth. This was the sacrificial shield doing its job. It was absorbing the kinetic energy of billions of cubic feet of air moving at lethal speeds. Inside the hut, the silence was absolute. It was a disconnect that was almost hard for the human brain to process. You could see the structural ribs of the barn vibrating through the small, triple-paned observation port we had installed in the hut's end wall. You could see the dust being shaken from the rafters of the barn, but you couldn't hear it. The 3 inches of closed-cell foam and the 18 inches of stagnant air acted as a perfect acoustic decoupler. It felt as though we were in a submarine, drifting through a dark, violent ocean, perfectly insulated from the crushing pressure outside. By midnight, the temperature outside had hit the baseline of -40 degrees Fahrenheit. At this temperature, the scales of Celsius and Fahrenheit actually meet. It is a point where the physics of cold change. Steel becomes brittle. Rubber shatters like glass. The very moisture in the air sublimates directly into ice crystals, creating a whiteout so dense that even a high-powered searchlight cannot penetrate more than 3 feet. This is where the Bernoulli effect usually kills a standard building. As the 70-mile-per-hour wind screams over a normal roof, it creates a massive pressure differential. The air moving at high speed over the top of the house has a lower pressure than the still air inside the house. This creates a powerful lifting force. But more importantly, it creates a vacuum that literally sucks the warm air out through every crack, every outlet, and every nail hole. In a standard house, you can feel the heat being pulled out of the rooms. The furnace can't keep up because it's fighting a losing battle against physics. But inside the Matryoshka fortress, the Bernoulli effect was broken. The wind was screaming over the barn, creating that vacuum on the outer shell. But the air inside the barn, the air in our 18-inch Plenum Space, was not moving. Because there was no high-speed air moving across the surface of the Quonset Hut, there was no pressure differential. The heat inside the hut had no reason to leave. The wind was trying to suck the heat out of the barn. But the barn had no heat to give. It was already cold. Here's what everyone missed. The sacrificial nature of the barn means it doesn't matter if the barn is minus 20 degrees. As long as the air is still, our R-value 21 insulation performs at 100% efficiency. In a normal house, wind chill can effectively reduce an R20 wall to an R5 by stripping the boundary layer of air away from the siding. In our system, the R-value remained constant. The numbers don't lie. And the numbers showed that even at minus 40 degrees, our diesel heater was only running at 30% capacity. It was idling through the worst storm in 34 years. Around 2 in the morning, the storm reached its peak. A gust, later estimated by the regional weather station at 82 miles per hour, hit the broadside of the barn. The entire structure shifted, a fraction of an inch, and a sound like a gunshot rang out. It was a galvanized bolt shearing off in the outer cladding. For a second, the dread returned. If the barn failed, if the shield was ripped away, the hut would be exposed to the full, naked fury of the Arctic. We grabbed the thermal imaging camera, its screen glowing a ghostly purple and orange in the dim light. We pointed it at the inner surface of the Quonset arches. We were looking for ghosting, for those telltale lines of blue that would indicate a thermal bridge or a structural failure. But the screen showed a sea of solid, vibrant orange. The interior temperature of the steel ribs was a perfect 71.8 degrees. The foam was holding. The seals were holding. We then turned the camera toward the observation port, looking out into the barn's plenum space. On the screen, we could see the heat signature of our own vent pipe, a bright, white-hot line cutting through the deep blue of the barn's interior. We could see a tiny amount of heat, a faint yellow glow, leaking from the door seal of the hut. But that was it. The containment was almost total. Let that sink in. Outside, the wind chill was pushing the perceived temperature down toward minus 80 degrees. A human being would suffer frostbite on exposed skin in less than 60 seconds. The barn was a chaotic, freezing wasteland of vibrating steel and screaming wind, and yet, just 18 inches away. We were sitting in a room where the air was so still you could see the steam rising from a cup of coffee in a perfect, vertical plume. It was a moment of profound technical clarity. We weren't fighting nature, we had simply opted out of the fight. We had used the geometry of the arch and the physics of the nested envelope to create a pocket of reality that the storm could not touch. The galvanized zinc. The material we once feared as a heat sink was now our silent guardian. It was reflecting the radiant heat of the concrete back into the room, while its outer surface remained blissfully unaware of the wind chill. As the sun began to rise on the second day, though rise is a generous term for the dim, gray filtering of light through the blowing ice, the storm showed no signs of relenting. But the anxiety had evaporated. We had passed the Matryoshka audit with flying colors. We began to track the fuel consumption. Over the first 24 hours of the blizzard, we had burned exactly 4.2 gallons of diesel fuel. Think about that for a second. To keep a 16 by 36-foot structure at 72 degrees in a minus 40-degree hurricane, we used less than 5 gallons of fuel. In a standard, unnested Quonset hut, we would have burned 20. The engineering had paid for itself in a single day. But more than the fuel, it was the psychological victory. The Quonset Hut. That 1941 relic of wartime necessity had been successfully resurrected as a 21st century lifeboat. We had proven that you don't need a massive, high-tech bunker to survive the end of the world. You just need to understand the way heat moves, the way air settles, and the way a single arch can hold back a mountain of wind. But as the wind continued to howl, we knew we couldn't stay inside forever. The snow was piling up, drifts of fine, crystalline powder that were already 10 feet high against the north side of the barn. Eventually, we would have to face the world we had spent so much energy hiding from. We would have to see what was left of the landscape after the 34-year storm had finished its work. And we would have to ensure that our invisible killer, the carbon monoxide we had worked so hard to vent, hadn't found a way to bridge the gap as the snow began to bury the barn itself. The physics of survival never truly rest. Even in the silence of the hut, the audit continues. Every hour, we checked the sensors. Every hour, we listened to the drone of the heater. We were the operators of a very small, very warm machine, drifting through a very cold, very white void. And for the first time in our lives, the numbers were exactly where they needed to be. By the 36th hour of the storm, the data began to tell a story that the wind was trying to hide. To the casual observer, the blizzard was a chaotic, unmeasurable force of nature. But to the sensors we had embedded within the layers of the Matryoshka system, it was a series of predictable, thermodynamic events. We had placed 12 K-type thermocouples at various depths throughout the structure, from the outer skin of the barn to the very heart of the hut's concrete slab. Now, as the blizzard reaches its absolute crescendo, we are finally ready to look at the receipts. The numbers don't lie, and what they reveal is a total breakdown of conventional construction logic. Outside, the world is a monochromatic nightmare. The mercury in the primary exterior sensor has bottomed out at -40 degrees Fahrenheit, but that is only half the story. When you factor in the 75-mile-per-hour gusts, the wind chill equivalent is plummeting toward -85 degrees. At that temperature, the physics of heat loss change from a linear progression to an exponential one. And yet, as we look at the sensor inside the barn's Plenum Space, the air gap between the outer shield and our inner living core, we see something that defies standard HVAC expectations. The temperature in that 18-inch void is holding steady at 17 degrees above zero. Think about that for a second. We have created a 57-degree temperature differential without a single active heating element in that space. The barn, which is effectively just a thin steel box with zero insulation, is acting as a heat trap. It is catching the minuscule amount of thermal radiation that manages to bleed through the 3 inches of closed-cell foam on the hut, and it is holding it. Now, picture this. You are standing in the center of the Quonset Hut. The floor, that 6-inch concrete slab we poured with such meticulous care, is radiating a steady 71 degrees. The air at chest height is 72 degrees. The ceiling, even at its highest point in the center of the arch, is 74 degrees. In a traditional peaked roof house, the temperature at the ceiling would be 85, while your feet would be freezing at 55. But the curved geometry of the Quonset Hut, combined with the airtight seal of the spray foam, creates a natural convection loop that keeps the air perfectly mixed. We have achieved a vertical temperature variance of less than 3 degrees. Here's what everyone missed. The true victory isn't just the warmth, it's the efficiency. We have been monitoring the fuel intake of the diesel heater with a digital flow meter over the last 24 hours. As the storm raged at its most lethal intensity, we consumed exactly 4.2 gallons of fuel. To put that in perspective, a standard modern home of this square footage, exposed to these same conditions, would have burned through nearly 25 gallons of propane or 15 gallons of heating oil. By nesting the structures, we have effectively reduced our energy footprint by nearly 80%. We aren't just surviving. We are thriving on a fraction of the resources. We pull up the thermal imaging camera one last time to conduct a final audit of the end walls. These are the weak points of any Quonset hut, the flat vertical faces that aren't protected by the strength of the arch. On the screen, we see the 2x6 framing and the mineral wool bats appearing as a sea of calm, cool green. There are no hot spots, no leaks, no thermal bridges. The internal air pressure, which we have kept at a slight positive relative to the barn, is preventing any of that minus 40-degree air from pushing its way inside. It is a mechanical stalemate, and the storm is losing. As we sit there, watching the data points stabilize into a flat line of thermal security, the engineering ceases to be a series of calculations and becomes a philosophy. We have spent the last 72 hours inside a 1941 design that was originally meant for the battlefields of the South Pacific. But by applying 21st century thermodynamics and the ancient logic of the Matryoshka doll, we have turned a military relic into a lifeboat. Let that sink in. The Quonset hut is more than just a building. It is a geometry of resilience. It is a shape that refuses to catch the wind, a shape that sheds snow like water off a duck's back, and when nested inside a secondary shield, it becomes the most efficient survival envelope ever devised. But this success carries a heavy responsibility. The very factors that make this system work, the airtight seals, the stagnant air gaps, the mechanical containment are the same factors that make it dangerous if you ignore the laws of chemistry. This is the lifeboat philosophy. A lifeboat is only a sanctuary if you know how to operate the valves. If you build a structure like this, you must respect the air you breathe. You cannot take shortcuts with your combustion air or your exhaust venting. You cannot ignore the silent threat of carbon monoxide pooling in your Plenum Space. You must be the engineer of your own survival, monitoring your sensors as if they were the gauges on a submarine. Because in a 34-year storm, there is no one coming to save you. You are the captain of a very small, very warm, very isolated ship. Think about the world outside for a second. The grid is likely down for miles in every direction. Traditional homes are being stripped of their heat by the Bernoulli effect. Their pipes are freezing. Their roofs are groaning under the weight of 10-foot drifts. And here we are, in a 19th century barn, inside a 20th century hut, living with 21st century comfort. It is a triumph of the structure within a structure methodology. As the sun begins to break through the clouds on the third day, casting a blinding, crystalline light over a landscape that has been completely reshaped by the wind, we step out into the barn. The air in the plenum is biting. It smells of frozen dust and galvanized steel. But as we look at the Quonset hut, sitting there like a silver egg inside a wooden nest, we realize that we have witnessed something profound. We have seen the numbers hold. We have seen the math stay warm. The Matryoshka Protocol is not just about surviving a blizzard. It is about a fundamental shift in how we think about the thermal envelope. It is a rejection of the idea that we must fight the environment with raw power. Instead, we have used the environment against itself. We use the cold, still air to insulate our heat, and we use the thin steel of a barn to break the back of a hurricane. If you have watched this audit to the end, it is likely because you understand that the old ways of building are no longer enough for the world we are entering. You realize that self-reliance isn't just about having a garden or a generator. It is about understanding the physics of the space you inhabit. If you want to see more deep dives into the mechanics of survival engineering, if you want to see the blueprints, the sensor layouts, and the thermodynamic audits of our next projects, hit the subscribe button and join this community of builders and thinkers. Because the next storm is already forming, and the numbers don't lie. We leave the hut now, stepping out into the waist-deep powder of a world that has been scrubbed clean by the ice. The air is so cold it feels sharp in the lungs. But we aren't afraid of it anymore. We look back at the barn, a simple, weathered structure that looks like any other farm building in the county. No one would ever guess that hidden inside its rough timber frame is a high-performance lifeboat, a thermal fortress that just laughed at the worst storm in 34 years. We take one last look at the exhaust vent, a steady, translucent plume of heat, rising into the freezing blue sky, and we head back inside. The coffee is still hot. The concrete slab is still 72 degrees. And the Matryoshka audit is officially closed. A perfect, undeniable success of engineering over chaos. Stay safe, stay warm. And remember, in the face of the elements, math is the only thing that doesn't freeze.